Okay, welcome to this presentation. I work with the loud guys over there. I've been working on Linux kernel for a while, and the past year or two, one of the cool projects that I've been working on is RealTime KVM, where Louise and Stefan and some other people and we've been working on getting KVM to work for real-time response times. Now, the first thing, of course, a lot of people imagine they know what real-time is. And they tend to have it mostly right. So there's a quick intro slide on there explaining what real-time is. And another issue that we see a lot with people trying to use real-time is that they imagine that their computer just works and all they have to do is run special software to get real-time. Unfortunately, that is not always the case. I'm also going to explain the hardware pitfalls in real-time. I'm going over what the real-time preempt Linux kernel patches do. We had to make a few changes in QEMU in the code. This might not be as interesting to some of you. And the configuration. When it comes to real-time, a lot of the magic is not in the code, but in the way the system is set up. I will spend a fair amount of time in that. And performance numbers are looking pretty good. Louise has been working really hard on keeping that from regressing and keeping the numbers better than we ever imagined. Well, real-time. A lot of people imagine that real-time is about speed. Something happens, you need to react to it instantly. And for some classes of real-time, that is absolutely true. But for some things like audio processing, sometimes you care more about having super high average latency. And if you have a little spike in your audio once a day, that might be perfectly acceptable. On the other hand, if you are a phone company, you might be fine with slightly higher average latency. But the maximum latency that you have happen is absolutely the single most important thing out there. Because if you have 50 million customers and 100,000 of them get some artifacts in their voice breaking up every week or so, they will switch to a different telco and you lose customers. The maximum latency is much more important than the average latency for many cases. Stock trading has a similar thing where if you let requests by one customer get ahead of requests that were filed earlier by a different customer, you might end up paying a very large fine, even if your violation of the rules was caused by a software bug. And even if the software bug was created by somebody else, like me, and not by people at the trading firm. So maximum latency, again, is super important there. And the same is true for controlling vehicles, like airplanes or rockets, where if you're trying to launch a rocket into space and you wait for a little bit on garbage collection, your rocket will twist out of control and it'll fly somewhere else. Or if you're the military, your rocket might simply explode at the wrong time, and it might as well not have exploded at all. You're not on the target, who cares? And applications may have many thousands of deadlines a second, so for a lot of markets, telco and financial, they want low latencies on the order of a few dozen microseconds. Maximum latency. The minimum and the average latency may be a lot lower than that, but that's not too important. They care about the maximum latency, and they care about knowing for sure that when a request comes in, it is handled within some deadline. It might be 10 microseconds for some people. It might be 50 microseconds for other people. It might even be 200 microseconds for some people, as long as they know that every single time the request is handled within that amount of time. So if we compare the regular kernel for RHEL 7 with the real-time tree and the KVM real-time tree, the regular kernel here is shown in red. The regular kernel is a lot simpler than the real-time kernel, so most of the time the regular kernel is actually faster than the real-time kernel. The average latency, the minimum latency, they'll be way down there. They're hidden behind the green graph. But you can see a few spikes in the red graph, which are totally unacceptable to people who need real-time. And the green and blue might be slightly higher on average than the average for the normal kernel, which is the red graph. But never having an unacceptable latency spike is what real-time is all about. And well, the green one is the real-time kernel running on bare metal. The blue one is a real-time kernel running on top of KVM, which runs on top of a real-time kernel on the actual machine. So latency inside a virtual machine is obviously going to be higher than running on bare metal, but we have managed to keep the maximum latency in the system at a level where people are happy with it. Now, a lot of the issues there are actually in the hardware, not in the software. I mean, for people who want these slides, they are available online, both on the Linux Foundation website and on my own. So you can just download them later on and have them in full quality. Well, the biggest problem, as usual, is the BIOS and all the different parts of the BIOS. Specifically, system management interrupts are a huge problem. Some hardware, we have seen things like the processor gets too warm, the BIOS traps the whole system into system management mode, and all of the CPUs in the system are stopped. They no longer run the operating system. Then the BIOS will do something like increase the velocity of the fan. And when it knows that the fan is now running faster, or at least enough current has been sent to the fan, a voltage has been changed, etc., that it will be running faster really soon. At that point, the BIOS will exit system management mode, and it will finally start running the operating system again. And in some cases, it can take several milliseconds. So you may be running software that can handle every request that comes in 5 microseconds. But if your hardware every once in a while goes on an extended vacation to change the speed of the CPU fan, you are not going to be able to hit your 5 microsecond response time. You'll be waiting for several milliseconds. So in this kind of a situation, when the hardware is not cooperating, you need to change settings in the BIOS, or in some really bad cases, you may have to put your system back in the box, send it back for a refund, because you are going to need a different piece of hardware. Not all systems can handle really low latencies. And well, once the hardware pitfall is out of the way, the next pitfall is Linux itself. Linux, like most other operating systems, also has sections in the code where the kernel, it takes a lock and it goes off to do something, and it does some more, and it does some more stuff, and eventually it releases the lock. And at that point, that CPU can start scheduling again, and it can start doing other things. It works really well for most use cases. But sometimes the particular lock or a particular other form of critical section where preemption is disabled, interrupts are disabled, it can cause latencies. And only after critical section is over, can you run your real-time program? So people have been working on resolving that issue by making the critical section shorter and by changing the way locking is done in the kernel. Stephen Rostad over there has been working on that for years, and as a result, Linux actually works really well as a real-time operating system.
You also forgot priority inversion.
It's in there. Yeah, go ahead.
So do you know the main reason why they don't take some of the patch with the configure like preempt RT?
Oh, a lot of the preempt RT code is already in the upstream kernel.
Yes, but there are some, right?
Yeah, and they're slowly going in bit by bit. Maybe Stephen has some more info on that.
Okay, I'll just say real quick. The reason why what we're doing, there's a lot of hard things that are designed in the kernel right now that we have workarounds for, but to us, those workarounds are not good enough to go upstream. We actually have to go in and redesign parts of the code within the systems. Like hot plug right now is a complete mess. Everyone knows it's a complete mess, but no one wants to touch it. So we actually have to go in and fix it. And everyone will be happy if we go in and fix hot plug, because it'll solve a lot of other problems, but then it makes real-time work. So basically, there's a lot of issues throughout the kernel that we have in the real-time patch. We have workarounds for, but those are workarounds. So although we can still get the same result, they're not going to be maintainable for a long run. So we have a high bar for what goes into the kernel. So we're picking things off slowly, but there's like lots of little things, and each time, so that's why the kernel for the last 10 years is becoming much better by the real-time patches work, but it takes time. That answers your question.
And as you can see, a lot of the real-time stuff is already upstream. The real-time scheduling policies in the Linux kernel, having support for kernel preemption, priority inherence mutexes, I'll go into that in a bit. High-resolution timer came from the real-time project. Long ago in Linux, if you wanted to sleep for a certain amount of time, you only could get woken up when there was a timer tick. And now, with the high-resolution timers, you can sleep for an arbitrary amount of time, and you can get waken up in between when timer ticks are happening by the system programming a timer to wake up at just the right moment. Pin lock annotation is a big thing that went upstream. Now its full mode is upstream. But some of the last bits of full real-time preemption are still in a separate tree, and bit by bit they are going upstream. A goal of the project is to make sure that all the real-time code ends up in the upstream kernel, and that all the remaining critical sections in kernel execution are either preemptible or very, very, very short. Well, the biggest goal, of course, in a real-time system is to have the highest priority task run right when it wants to run, without waiting on anything else to finish doing what it is doing. Which could be things like lower priority tasks, it could be spin locks, it could be interrupts, or it could be interrupts being blocked and stopping the timer from coming in and waking up your high priority task. How does it do all of those things? Go ahead.
So we are talking about the real-time patch in the Linux kernel. You mentioned like a very, very short time. Do you have like some guaranteed short time? Like, okay, give me a machine, like it will click up to a threshold. Do you have some theoretical guarantees to achieve that, or it's just okay, hope for the best, like 99% of the time is very short, or 99.99?
No, the measurement is done at 100%. But in that, I also have to be honest in that we cannot measure every possible thing that everybody would like to do. So there are certain things that have been measured, and we make sure that they remain fast. And a typical test run is 24 hours, where we run a particular test, and we do not allow any latency over a threshold within a 24-hour period. So it's not just a 99 or a 99.9% guarantee. We want it to be 100% guarantee. And, well, one of the big things that has been done is changing spin locks into priority inherited mutexes. So everything that is a spin lock in a normal kernel and held by a CPU is now a sleeping lock that is held by a task. And a few data structures are still classical spin locks because you need things like the scheduler to be able, and the timer interrupt, to be able to wake up tasks and manage the data structures where running tasks are sitting. And those need to be still classical spin locks. And those are called raw spin locks. And if you look in the kernel, you can see some places call spin lock particular lock, and other places might call raw spin lock of a lock that was declared as a raw spin lock. In a normal kernel, these two are exactly the same. In a preempt real-time kernel, they are totally different locks. And a lot of the annotation of the locks is already upstream, and you may wonder, hey, why are these two locks named differently when they do the same thing in a regular kernel? And well, now you know that they are totally different in a real-time kernel. A big thing is priority inheritance, where you might have 3 tasks running on a particular CPU. You have a low priority task that it does something and it grabs a lock in the kernel, and then it gets preempted because you have a slightly higher priority program that wants to run. And then a medium priority program gets interrupted again when your highest priority program in the system wants to run. And if that highest priority program now wants the lock, it needs to wait for a lower priority program to maybe at some point in the future run and release that lock. That's a problem with real-time. And that is fixed with something called priority inheritance, where the highest priority program waiting on a lock will temporarily give its priority to the program that is holding the lock. And a program that is holding the lock can then keep that high priority until the lock is released. And then immediately the higher priority program will grab the lock and continue running on its own thing. And this is something that really helps a lot and allows the people on bare metal real time to keep their latencies single digit microseconds in every single case. Another thing that helps with that is RCU is no longer something that stops CPUs from scheduling, or tasks from scheduling. And most interrupts are run in threads that can be preempted when something else needs to run. Well, hardware real-time is pretty complicated. Once you add in virtualization, it gets slightly harder. And Louise and I have been working on that for the past year or two. But we've got it working. And some of the issues are that things like priority inheritance do not work between a guest and a host. Because if you have your virtual machine, it may have a certain real-time priority. You may give it priority 2, for example, in the host. Inside the virtual machine, you might have programs of various real-time priorities running. There might be something with priority 1, something with priority 2, something with priority 3. And it doesn't help because the host has no idea which of the virtual CPUs in a guest is running the highest priority program. It's not visible to the host. And we have thought about making it visible to the host, but it's not something we can actually do. Because if you are running a virtual CPU with a lower priority program, and the host decides to run something else. And at some point, a higher priority program becomes runnable on that real-time virtual CPU that is now not running, then we cannot inform the host that we now have a higher priority thing until it is running again. So it's kind of a chicken and egg thing, and we had to come up with a totally different solution for real-time virtualization. And housekeeping tasks that might take 2 microseconds in bare metal real-time. In a virtual machine, they might take a whole lot longer. First, because when the guest does that housekeeping thing, instead of writing to a single hardware register, you may end up first trying to write to a hardware register. Then the CPU realizes, hey, I am virtualized. I cannot do this. It traps into the host. The host has to emulate what is going on in software. And then after everything is done, the host can return into the guest. This is not too bad. But then, what if the host, due to bad luck, also tries to do the same housekeeping task itself? And the host and the guest both do the same 2 microsecond thing. It takes 4 microseconds in the guest. The host adds its own 2 microseconds, and suddenly you're looking at a 6 microsecond thing for something that used to take 2. So there were a number of issues there where we had to redo or change the way that housekeeping tasks in the kernel are done, because we do not want the host and the guest doing the same thing at the same time, and we'd rather not have them not do that at all. So some of the issues that were not an issue at all for bare metal real time, they became problems for us, and we had to solve those. Oh, and there was one other thing. When you're running on hardware and you have a low priority program that does anything, you can always interrupt it to run your higher priority program. Inside a virtual machine, this does not always work, because you may have some program in your virtual machine that tries to write to the graphics card. And the graphics card is emulated by a piece of software running in user space on the host. And emulation can be slow sometimes. And it's possible for a program running on a real-time virtual machine to start an operation that has to be finished on a different CPU on the host by a different thread running there, running on a CPU that might also have something higher priority on it. And if you have something like a program writing to a graphics card inside a guest, that could prevent that virtual CPU from doing anything else for hundreds of microseconds. So we found a solution for that, and I will get to that in a bit. We made a few kernel changes to real-time to make stuff work right. There were some small bugs in the real-time code that really were not an issue for bare metal real-time. Things like having the scheduler tick still enabled when you have one high priority and one low priority real-time task. And every millisecond, the kernel looks, oh, do I want to reschedule? Nope, I'm running something real-time, and the other thing is low priority. And every microsecond, it does that. It's perfectly fine if you run one kernel on bare metal. It's not perfectly fine if you have a virtual machine and a host both doing that thing at the same time 1,000 times a second. Some other small changes had to make to just make stuff work right, where having the host and the guest do stuff at the same time caused issues. Priority inversion, inheritance, they simply do not work in a virtual environment because we have a relatively clean abstraction between a host and a guest. And the host cannot see whether a guest is running something really important or whether it is running the idle thread, and it was started with idle is Paul. And we also run into the issue, if we do not know what the highest priority thing on a particular CPU is, that means we do not know whether the virtual CPU should be interrupted for a higher priority thing on the host, or whether the virtual CPU will ever stop running and we will finally get to run the lower priority thing on the same physical CPU in the host. And if we cannot do real-time scheduling because we do not know the priority of one of the things on a particular CPU, then we need a different solution. And the solution for that is to do some form of partitioning where the virtual CPUs that run real-time tasks of a guest have to run on what is essentially a dedicated physical CPU on the host. We boot the host with ISIL CPUs and no Hertz full. That means we do not get timer interrupts on those CPUs when the guest is running. And most of the kernel housekeeping tasks that it normally does on a CPU, things like RCU callbacks and various other random things, are now offloaded to housekeeping CPUs. And we have as few interruptions as possible for our real-time CPUs. And the interruptions that are remaining, they have passed our tests as being short enough that they do not inhibit the latency goal. So what it looks like is, no, go ahead.
So for the previous slides, if you do this static partition, what's the difference between the real-time KVM and the jailhouse?
The difference between real-time KVM and jailhouse is mostly that jailhouse aims for very small code base and limited functionality, and we try to be able to just run everything with the same code base that is also used elsewhere. And I don't know exactly if there are functionality gaps between the two for what people are actually using them for. I do know that with Red Hat, for example, we would like to support one code base and not have two different code bases and maybe have different security issues that we need to track in both. We have just one solution and one piece of code. We can make sure that the real-time people get the same level of support that everybody else gets. And if we have a totally separate code base, then it would probably get less developer attention, and we would not be able to look after it as well as having just one code base for everybody.
And can you support multiple VCP, real-time VCPUs on the same CPU?
No, if you always need low latency within one guest, you need to make sure that all the virtual CPUs of each guest are on different physical CPUs. And you could share a physical CPU with a non-real-time guest on the host side if you wanted to, but at that point, if the real-time guest misbehaved, then the other guest could see CPU starvation. So it may not be worth doing.
Yeah, if you have a bug in your CPU, even for the non-real-time case, like you can also starve other VCPUs.
Sure, but in real time, you could starve another vCPU forever, a lower priority thing. This is one possible configuration. There are other ways to do it. With newer Intel CPUs, you do not have to partition things on a socket basis at all, because they have a technology that I'll get into later that can partition the cache inside a socket. Inside the guest, we have similar issues where if you have a task inside a virtual CPU in a virtual machine that does something that it should not be doing, like writing to a serial port or a VGA card, you can hit a code path that has very slow emulation. And at that point, you cannot run your high priority real-time task until the slow emulation has finished. So we need the same kind of partitioning inside a guest as well. For the guest, we also boot with isol CPUs. The real-time tasks run on the isolated CPUs, and everything else runs on the system CPUs inside the guest. And I'm sure I could come up with a really confusing graphic that shows both in one, but I did not do that. Well, performance numbers. How well does it actually work? Kind of a complicated thing. But on the other hand, modern CPUs have a lot of cores. And both Intel and AMD have produced CPUs where if you were to run every single core in a system, or every single core in a particular CPU at full power at the same time, the CPU would catch fire. So it looks very wasteful to have dedicated cores for real-time, but on most of the really modern, the newer CPUs, you could not run everything at full power simultaneously anyway. You don't have the resources you think you have. So it's not as bad as it looks. The scheduling latencies that we have measured, I think some things that Luis did actually brought the maximum down to 13 microseconds. And the average is just a few microseconds. Do you know if the new numbers are much better than this or similar? Or?
More or less the same. I mean, it's getting left. But yeah, so it can vary now. 2 microseconds, I think it's 2 months more. It can vary.
Yeah, so yeah, well, numbers have gotten a little bit better. Go ahead.
2.6.
Well.
Those numbers can change depending on what hardware.
Oh, yeah, absolutely.
So it doesn't matter what hardware.
It's very hardware dependent, and it's easy to accidentally run into some kind of BIOS code that will give you 100 microseconds latency. And then you need to dig into the BIOS and figure out what is going on. And you have a tool to help detect whether that is happening as well. Now, if you look at the latency graphs again, the graph on the left compares normal RHEL 7 with a real-time tree and real-time tree in KVM. And you can see that the normal kernel has perfectly acceptable latencies most of the time. Just the maximum latency is totally unacceptable to some people. And the graph on the left, we have removed the maximum latencies to zoom in. And you can see that real-time KVM is a fair bit slower than running on bare metal in latency, as expected. But we can still get to around a dozen microseconds maximum latency. And running in virtual machines does have certain management advantages for people. And they might have an application that they built for a certain version of the OS. And they want to continue running that application inside the same version of the OS for the next 15 years. And they may change out the hardware under it and change out the hypervisor, but keep running the same OS with the same application because they know that works. And the maximum latency for real-time KVM is pretty low.
How the 6-7 microsecond numbers you were showing there, how would those compare to, say, a 486 system? Would we see 6 to 7 microseconds on that system, or would that be more in the 60 to 70?
That's a good question, and I don't know. I have no idea how much latency got better over the past decade or so in hardware. I mean, throughput has obviously improved a lot, but latency, there are some latency effects actually where you need some new technology that Intel has. You have the cache allocation technology where you can partition the level 3 cache. And you actually need that for some workloads because It takes about 80 nanoseconds, I think, to load a cache line of data in from RAM. And if you are running inside the same sockets, unconstrained CPU cache, and you have a non-real-time program running that makes a backup of the whole system on one core, and the other core is dedicated to a real-time task, the real-time task may find itself needing to load several megabytes of info from RAM into the level 3 cache. And there is no way you can do that in a dozen microseconds. And you actually need to do things like ensuring that most of the data you need stays in the level 3 CPU cache. Otherwise, you're too slow. And that means you either, on other systems, you would have to move things into different sockets, where the real-time stuff just sits on the socket together, and it competes only with itself, with each other. Or with the newer CPUs that have cache allocation technology, you can do the same kind of cache partitioning inside a socket. And well, there are a number of system operations that are known to cause high latencies. Things like CPU frequency change, CPU hot plug inside a virtual machine. Hardware hot plug is extraordinarily rare. Loading and unloading kernel modules stops the whole kernel for a little bit. You don't want to stop the whole kernel. You're doing real time. Moving tasks between isolated CPUs and non-isolated CPUs can cause latencies that are issues for some people. If you are running a real-time task on CPU number 7, for example, and you have some low-priority Java thing running on the system that has 500 threads that sometimes do something and they sometimes run somewhere, and one of them is the garbage collector and it does an mprotect call. And suddenly your low priority Java thing sends out a TLB flush to the CPU that runs your high priority real-time program. And once the TLB flushes are all done on all the CPUs, CPU 7 can go back to running the real-time program. Or, well, the flush will prevent your real-time program from being scheduled in if it happens to wake up while the flush is going on. And there are some things there where it makes sense to do some partitioning in the system to keep real-time and non-real-time things separated away from each other. Real-time also needs a very fast clock source. That means you need a system that has stable TSC. And you need a system where the TSC is not just stable, it gives you the same number on every CPU if you read it simultaneously. Having TSCs that are out of sync between different CPUs makes real-time really difficult. And the best thing to do is to buy a computer where the TSC gives the same value on every CPU.
That's not that easy thing.
Sure, but yeah.
We have some issues right now. Talking to a BIOS vendor or something like this.
Yeah. And, well, an obvious cause of non-real-time response is page faults. If your real-time program is swapping, it's no longer real-time. The solution is to have enough memory for your program. And a more subtle one is using slow devices. If you have a real-time program that writes something to disk, you may end up waiting on the file system, and you didn't really want to do that if you want a real-time response. And a solution for that is usually to split up the real-time application into multiple programs. And one program takes care of, say, the network transactions that have to happen in 10 microseconds. And a different, totally separate part of the program will log stuff to disk, because that is not something you want to interrupt your real-time responses for. Now we come to cache allocation technology. I think you can get CPUs with at least 20 cores nowadays. There might be more, maybe 22, not sure. But it takes a certain amount of time to load something from DRAM. And if your real-time program touches several megabytes of code and data, you can spend a lot of time just waiting for stuff to load from RAM. And there will be no piece of code that keeps your program slow. You're just waiting on RAM because your stuff is not in the CPU cache. And if you want 10 microsecond or even 20 microsecond latencies, you simply have to make sure that programs that use lots of memory do not get a chance to push your real-time programs out of the CPU cache. And this can be done by keeping things on different sockets or by getting the newer CPUs that have the cat stuff in them that allows you to partition the cache between different workloads, different cores. So you can have, out of your 22 cores on a socket, you might dedicate 16 cores to real-time stuff and give them 2/3 of the cache of that particular CPU. And you might have the other cores for everything else running on the system and give them only 1/3 of the CPU cache on that CPU. And other real-time programs will not suffer from having all of their data kicked out of the CPU cache by the other stuff running on the system. And this really helps improve the latencies. It's not a 100% guarantee, but if 99.9% of your stuff is still in the cache, it's only a tiny amount of data where you will suffer your 60 nanosecond access latency. That's not going to break your several microsecond real-time response. Let's start the conclusion with the biggest surprise. Real-time KVM is actually possible. We managed to get it to work. But it is done largely through system partitioning. And the overcommit that you may be used to from running virtualization in the cloud or from somebody else running virtualization in the cloud so you can rent a virtual server for $8 a month. That's not really an option for real time. You need some dedicated resources. We've got latencies down to about 12 microseconds for real-time tasks running inside virtual CPUs. This is the maximum latency. The average is a lot lower than that. And it is very dependent on hardware. You need to make sure the hardware does not break real-time responses. Virtualization is useful in real-time applications for some use cases where people need some more isolation or they use it for manageability, hardware compatibility, things like that. But the configuration needs to be done very carefully. And luckily, we're working on automation. So things like OpenStack and Rev can do a lot of the hard work for people and set things up the right way. Take some of the guesswork away from system administrators. And another thing to look at is a tool called the hardware latency tool that is used to test bare metal to see if a system is actually capable of running a real-time workload with low latencies.
Is that why I have patches out to make that into one of F-Tree's tracers?
Oh,
and I'm
excellent.
putting that for 4.9.
Okay, so things are coming up to turn the hardware latency tool into a tracer. That's really nice. Great to hear that. That's really nice. And we have a few minutes left for questions and answers before the end of this session. Are there any other questions? Oh, go ahead.
Just to let you know, like this is actually more of a sales pitch type of thing. A lot of this thing that we're pushing at is like, yeah, we're trying to hit how we work on how low latencies we can get. But real time just really means deterministic worst case scenarios. So if your real time task only requires like 1 millisecond latencies, and you can do everything within that. Well, lot of these things that we specialize are not required. So we're showing you like kind of the extreme. What Rik's here is like the extreme, getting down to sub 100 microsecond latencies and such. That requires tricks. But if you do have an application that doesn't require that strict of worst case scenarios, a lot of the stuff you can actually just run and still it'll work.
Yeah, that's a good point. And it certainly keeps people's lives easier.
I have a question about the latency data here. So when you are running the cyclic test, are you running multiple threads on all of the vCPUs for the real-time VM, or you are just running one?
I think Luis is probably the best person to answer that.
Yeah, so we test both things actually. We test one thread, and then the maximum test was 6 real-time threads, not 8 CPU, and it increases a little bit, but it's below 20 microseconds.
Did you try
another test case is also multiple VMs, and then we also have the test case, and it's also more or less the same thing.
Did you try to run? Suppose you have ARM vCPUs. Did you try to run ARM threads on all of the vCPUs and see what's the maximum latency?
No, you're not getting it.
So did you try to run one cyclic test thread on each real-time vCPU?
It was like one cyclic test on each real-time CPU.
Yes, yes.
That's what you guys do, right?
Yeah,
No, you run 6. You run 6 on 8.
Yeah, because the answer is yes, because cyclic test has actually multiple memory threads. So, it's what you get is multiple memory threads.
Yeah. I ran them before.
It should be the same, yes. Right?
It's one on each CPU. It'll spread it out on all the real. You say I want to run on all these CPUs, and it'll run a real-time task on each of those.
Yes, yeah. So I'm just wondering because even for the multiple threads case, right? You run 6 threads on 8 vCPU VM. So basically, I'm assuming you kick out all of the system service to the other 2 other vCPUs. I'm just wondering what if you run a real cyclic thread on that vCPU and see how much interference it may get.
So it's the partitioner we talked about. So we separate the system into housekeeping CPUs and real-time CPUs. The housekeeping are not going to run cyclic tests.
So you have to waste one.
Repeating too, because they do housekeeping. They're not supposed to run the real-time test. So
I think we probably need to take that discussion out into the whole way, since we just got the 1 minute sign, and we can do a few more questions.
About the host is not aware of the priority of the guest. Did you try or research if sharing the priority of the task that is running on the vCPU with the host improves the situation? So basically, if, for example, the guest makes a VM exit and somehow, I don't know how, signalizes the KVM and the QEMU that it has currently running the thread of this priority, this kind of pass, is it too hackish or by itself?
One issue may be who in the guest sets that field they share with the hypervisor. If you're not running, you cannot change that field.
Yeah, but the tasks are changed only when they are there.